Hello, my name is Fabio. I'm a postdoc at the University of Helsinki, Finland. And today I'm going to talk about this work in progress in the water mass transformation on the Antarctic continental shelf using an ocean ice shelf model. So basically, the Antarctic continental shelf is an important site for the origin of Antarctic bottom water, the densest water mass in the global ocean. And that's thought to originate from high salinity shelf water, which results from brine rejection at coastal polynyas around Antarctica. And the high salinity shelf water basically mix with other water masses sitting on the continental shelf and ultimately overflow to the abyssal ocean as Antarctic bottom water. The floating Antarctic ice shelves are also an important source of water masses. So basically, basal melt can be induced by intrusion of water masses below the cavities, and this can be caused by intrusion of high salinity shelf water or circumpolar deep water or even surface waters. And that's ultimately produce an ice shelf water, which has surface temperatures below surface freezing point and a low salinity. This work basically, you are trying to investigate the process and dominate the interaction between high salinity shelf water and ice shelf water. And for that, you use this water mass transformation framework. So apply that for the continental shelf and try to investigate all the driver mechanisms of these transformation rates. And you also evaluate the sensitivity of our results to model resolution, tidal forcing, and topographic resolution. So for this study, we use a circumpolar Antarctic setup of the regional ocean modeling system called Whole Antarctica Ocean Model. And this setup is configured with 3 different resolutions. So then basically we have a model setup with 10, with 4 and 2 kilometers. The model includes tidal forcing from TPXO, lateral boundaries are forced by echo-2 reanalysis, and surface winds are from air entering. And as the model doesn't have a sea ice component, we force the surface heat and salt fluxes with sea ice estimates from satellite observations, which actually has a good representation of the fluxes at the coastal polynyas where high salinity shelf water originates. And all the ocean sea ice interaction follow, ocean ice shelf interactions follow the 3 equations parameterization from Holland and James. The experimental design, we chose to simulate a repeat year forcing to represent a mean state. So we based it on the year 2007. And each individual experiment has different lengths. That was an attempt to use the spin up from the coarse resolution to start the high resolution experiments. So basically the 10 kilometer setup was run from 20 years. The 4 kilometer setup was run from start from the year 10 of the 10 kilometers and was run for 10 years. And the 2 kilometer setup will start from year 5 of the 4 kilometers and run for 5 years. And all the reanalyses that you're going to show are based on the last year of each experiment. And here you show the time series of the ocean heat content and salt content, the 2 top plots integrated over the continental shelf, just to show the approach of each experiment to an equilibrium state. And in the bottom, we have the time series of the mean kinetic energy for the entire domain. So that kind of shows the stability of the ocean currents, which are achieved at a few simulated years. So talk about a bit the water mass transformation framework. This framework in density space, which is what you used here, describe the net transformation of water mass towards lighter or heavier densities for each individual density class. And using the heat and salt budgets, you can decompose that into contributions from individual physical processes, such as advection, diffusion, or surface fluxes. Basically, we obtain all these budget diagnostics from the model with temporal resolution of 5 days. And these are described in the first 2 top equations. So the total, basically total net salt tendency in the left, which is the sum of the local and advective components, are equal to the horizontal and vertical diffusive components. And then you combine the heat and salt budgets through density equations. So the 3rd equation here from top to bottom, which all the individual terms are multiplied by either the heat expansion or the salinity contraction coefficients. Then you use this delta function to bind all the individual terms into density intervals. And then we integrate these terms vertically throughout the mixed layer depth and horizontally. And that results in this omega function, which actually describe the transformation rates for each density classes. So go straight to the results. We first look at the contribution from the heat and salt budgets to the total water mass transformation over annual mean and integrated throughout the whole Antarctic continental shelf. So basically, in the top row, you can see that the surface heat flux in magenta drives transformation towards denser waters, but it's compensated by an opposite effect from diffusion, which is the blue line, and advection, which is the red line. And in the end, the net heat tendency is around 0, which means that the heat budget doesn't have a very large contribution to water mass transformation. And in the bottom row, we have the salt budget. So basically, you can see the magenta line again show the surface salt flux has opposite effects depending on the density. Basically, it induces buoyancy loss at density greater than 27.5 and buoyancy gain at densities lower than 27.5. The advection has a role to partially compensate the buoyancy loss from the surface flux at large densities, while the diffusion partially compensates the buoyancy gain at lower densities. The water mass transformation to salt density is non-zero in contrast with the heat budget, but it varies greatly among the experiments. So basically, the 10 kilometers resolution experience more buoyancy gain at lower densities and buoyancy loss at high densities, while the 42 kilometers only show buoyancy loss at higher densities, and that is actually larger than what you see in the 10 kilometers. And then to better understand what the difference in water mass transformation rates associated with the salt budget, where it comes from, we break down this into 2 meridional regions, basically dividing regions below the ice shelf cavities and the rest of the continental shelf, and 5 zonal regions, depending on these different sectors of the Antarctica. So basically, at all resolutions, we find that the buoyancy gain occur mainly in the Ronne-Filchner ice shelf, while buoyancy loss occur in the continental shelf from pretty much every zonal subsection, which is expected to be linked with this presence of coastal polynyas and high salinity shelf water formation. So the larger buoyancy gain that you see in the 10-kilometer experiment come mostly from this Ronne-Filchner ice shelf, and you're going to explore the mechanisms in the next slides. To understand the role of the individual process, the individual process such as advection, diffusion, and surface fluxes to the total water mass transformation associated with the salt chains. We look at the maps of the water mass transformation integrated over different density class. So basically, these maps are constructed by evaluating the transformation rates before the horizontal integral in the omega equation. So basically, integrate the transformation maps throughout the peak of the buoyancy gain, the 10-kilometer experiment. And also here we include a comparison with the steady state melt rates from Rinot 2013. And you showed here that the positive and negative melt rates below the Ronne ice shelf is comparable with negative and positive transformation in the maps, which actually showed that the model had a good agreement with some observations. So the transformation rates due to the salt flux, which is that right column here, have a similar geographical distribution among the experiments, but there is an increase in the intensity with increased resolution. So the contribution for diffusion basically opposes the negative transformation rates due to the surface flux. And this can be interpreted as fresh water melting, being mixed due to the diffusive process. But the advective process differs quite a lot between the resolutions. At 10 kilometers, advection largely induces buoyancy gain, while at 2 and 4 kilometers, large areas are instead experience buoyancy loss, especially between the hairy and coarse ice ridges. And in the end, advection is actually the main driver of the total net salt tendency. And then to investigate better the whole of the advection to the differences across resolution, we look at the bottom temperature, salinity, and bottom currents. And what you can see here is that the 2 and 4 kilometers, or the 2 bottom rows of the right plots, experience warmer and salt waters penetrating the Ronne Ice Shelf throughout the Ronne Depression in the west, and that spreads south and eastward, which are basically in agreement with the circulation of high salinity shelf water that you know from observations. And this intrusion of warm and salt waters is closely related with the circulation north of the ice front. There's a quite strong anticyclonic circulation between the Ronne and Hugh troughs, and that's much stronger in the higher resolution experiments at the 42 kilometers. And this circulation helps to bring some warm and salt water from near the shelf break to below the cavity. And when you look at the surface, TS properties and currents, we see that most of the warm water intrusion actually occurs through the bottom layer, and the surface currents are much weaker. It still has this anticyclonic circulation, but are much weaker than at the bottom layers, suggesting a role of baroclinic circulation here. And even though the temperature difference are smaller, there is a substantial freshening at high resolution, which it actually indicates that the warming is enough to cause basal melting. And then when you look at the surface salt flux maps again, that clearly indicates transformation towards light density in the west side of the Ronne Ice Shelf that extend eastward near the ice front. And at the same time, the buoyancy gain with the basal melt increase with the resolution. It also enhanced the buoyancy loss associated with regions of refreezing, especially between this area between the Corf and Henry ice ridges. Next, we look at some transects under the Ronne Ice Shelf, one in the west flank where warm water penetrates, and another one towards more to the center, crossing this region between the Corf and Henry ridges. So basically, a salinity cross-section in the west portion of the Ronne Ice Shelf showed a baroclinic structure of these water penetrations with salt water penetrating on the bottom layer and a fresh plume on the top. And while the cross-section in the central ice shelf shows salt water occupying a mid portion of the cavity, while there is well-mixed column observed near the ice front with fresh water and above the topographic rise with salt water. Then when you look at TS diagrams, you can clearly see that there is more warm and salt water penetrating under the cavity with increased resolution, which actually cause melting that originate waters with near freezing temperature and low salinities. And in the bottom right part of these TS diagrams, you can see waters with temperature close to the freezing temperatures at the base of the ice shelf, so roughly between 400 and 500 meters depth in average. And these have quite high salinity, especially in the central transects. So these are actually characteristics of freezing water that are occurring in this area between the Henry and Corf ridges. The last part here, we investigate the sensitivity of all these results to the tidal force and bathymetric resolution. So we use the 4-kilometer setup to conduct one experiment without tides and another one using a coarse 10-kilometer resolution bathymetry. And basically, you see that here that the experiment without tides is much cooler and fresh in the west flank of the Ronne Ice Shelf, which results from a substantial weakening of this anticyclonic circulation. And while this circulation is associated with a topographic elevation, it's highly driven by tides. And in contrast, the experiment with coarse bathymetry it's not that different from the original experiment. Basically, you can see these warm salt waters in front of the Filchner ice shelf, towards the east. But the anticyclonic circulation and intrusion of warm salt water in the west part of the Ronne ice shelf is not much different. And when you look at the transformation maps on the ice shelf, you can see that without the anticyclonic circulation in the low tide experiments, the transformation associated with melting near the ice front is strongly reduced, and the water mass transformation with the melting and refreezing in the regions of the cavity also decrease greatly. Also, without tides, the advective component of the water mass transformation is significantly smaller, and the net transformation is basically near zero below the cavity. And on the other side, the water mass transformation rates in the low resolution bathymetry experiment is not so different from the original experiment. So positive transformation associated with freezing near Henry and coarse ridges slightly decrease, indicates some dependence of the bathymetric details, but the transformation rates are quite similar, and that indicates that resolving the physical dynamics associated with high resolution solution is more important to water mass formation below the Ronne Ice Shelf than having a high resolution bathymetry. Just to summarize, so this work will show the water mass transformation on the Antarctic continental shelf is actually dominated by the salt budget. So process of high salinity shelf water formation are less sensitive to model resolution in our setup, where this observational based sea ice fluxes is primarily important for high salinity shelf water formation. But the model resolution has substantial impact on the water mass transformation rates below the cavities, especially in the Ronne-Filchner ice shelf. So there's this anticyclonic circulation that brings warm and salt water under the west flank of the cavity, and that enhances melting near the ice shelf, the ice front, with increasing, also increasing refreezing rates in this region between the Henry and Croft ice ridges. And this anticyclonic circulation, and therefore the water mass transformation rates, are strongly depending on having a high resolution physics and a tidal force. So these results indicate that high horizontal resolution and tidal force are quite essential to simulate realistic basal melting rates and water mass transformation rates under the Ronne Ice Shelf, and that can have a large impact on the transformation rates over the circumpolar Antarctic domain. Thank you.